Imagine a universe that only exists when you're looking at it, where the chair beneath you, the stars above, even your own hands, dissolve into a haze of probabilities the moment your gaze drifts away. This isn't the stuff of mystical poetry. It is, unnervingly, the reality hinted at by quantum physics. And it has left scientists, philosophers and dreamers staring into a riddle that stretches from the tiniest particles to the furthest edges of the cosmos. When no one's watching, does anything exist at all? It sounds like the sort of question you might ask in a philosophy class after midnight, when the coffee's gone cold and the room smells faintly of burnt toast from the vending machine's last attempt at food. But in the strange theater of quantum physics, this is not just a whimsical thought. It is a question we can, and have, put to the test. And the answers we've found are far stranger than any dream. The very act of looking, or not looking, can decide whether a particle is a wave or a bullet, whether it even has properties, or merely floats in a cloud of possibilities, waiting for someone or something to force it to choose. Imagine for a moment you are standing on the deck of a ship, adrift in an endless, silent sea. You have a spotlight in your hand, but the beam is thin, narrow, revealing only what it touches. Outside of that beam, darkness, not merely unseen, but perhaps unreal. In the beam's path, the world sharpens into detail, a railing, a coil of rope, a glint of water. But beyond it, you don't know if anything is there, and quantum mechanics suggests it might not be. For most of human history, we assumed reality was like a painting, a fixed canvas, fully formed whether we gazed upon it or not. The mountains didn't vanish when the traveler turned his head. The moon didn't cease to exist on a cloudy night. Existence was assumed to be absolute, independent of perception. But the quantum world does not respect these assumptions. It whispers something profoundly different, that the universe may be more like a vast, dynamic movie set, constructed moment by moment, scene by scene, depending on where and whether someone is watching. This idea didn't emerge from the mind of a poet or a mystic. It emerged from an experiment so simple in design and so devastating in its implications that more than a century after it was first performed, physicists are still debating what it means. We call it the double-slit experiment. And if you've never heard of it before, you're about to. If you have heard of it, prepare to see it in a way you never have before. But before we walk into that laboratory, let's sit with the implications for a moment, because this is not merely about particles or electrons or beams of light. It's about the bedrock of reality itself, about whether the universe exists as a definite something when no one is there to witness it. I want you to picture a single particle. Let's say an electron drifting silently through the void. You cannot see it, you cannot touch it. In our everyday intuition, that doesn't matter. We assume it's there, minding its own business, moving along a path that could be measured if we wanted to. It has a position, a velocity, a definite place in the grand game board of space. But the quantum world laughs at that assumption. It tells us the electron's position, before we look, is undefined. Not in the way a lost key is undefined, waiting to be found in the sofa cushions, but in a much deeper way. It is not anywhere. It exists as a spread of probabilities, a shimmering cloud of maybes. Only when we look does it decide where it is. And this is where things begin to feel personal. Because if particles are only real when measured, then what does that say about the rest of the universe? Is it quietly existing out there without us, or does it need us, or at least some form of observation, to solidify into being? Our story will take us through the key experiments that have tried to answer this. The double slit, the delayed choice, the quantum eraser. We'll meet the interpretations, the Copenhagen, the many worlds, each offering a different lens on whether reality is an independent truth or a co-authored play between the cosmos and its observers. And as we journey, I will ask you to do something unusual. Hold two contradictory thoughts in your mind at once. The first, that the world around you is tangible, solid, existing whether you pay attention to it or not. The second, that it might all be like mist, condensing into droplets only when you turn your gaze. Now, back to our ship on the endless sea. You switch off your spotlight. The deck fades away. You're left in pure darkness. You tell yourself the rope, the railing, the sea are still there. But in the quantum world without observation, their there-ness is not so certain. And if we scale that uncertainty down to the smallest building blocks, electrons, photons, quarks, the picture becomes even stranger. Because it's not just that you can't see them when you're not looking, it's that in some sense they aren't anything definite until you do. Here's where the universe becomes both a detective novel and a magic trick. The clues are real, the evidence is measurable. But the act of looking at those clues changes the ending of the story. Over the next hour, we'll unravel how a simple experiment, light passing through two narrow slits, can collapse centuries of certainty about the nature of reality. We'll see how physicists have tried to trap reality in a corner, only to watch it slip away like smoke, and we'll confront the possibility that the universe itself may be stranger than anything we've yet imagined. So settle in, because this is not just a physics lecture. This is a journey to the edges of knowledge, where science and philosophy touch fingertips, and where the answer to "do particles exist when you're not looking" might just change the way you think about everything. And to find our first clue, we'll step into a darkened laboratory in the early 1800s, where a beam of light, a sheet of card, and two thin slits will begin the most important and unsettling experiment in the history of science. The laboratory is dimly lit, oil lamps casting long shadows on the walls. The year is 1801. A man named Thomas Young is about to do something extraordinary, though he could not have known it at the time. His goal was modest, to answer a question about the nature of light. Is it made of particles, as Isaac Newton believed, or is it a wave rippling like sound through some invisible medium? Young's setup was simple, almost deceptively so. A beam of light directed toward a thin card with two narrow openings, two slits. Behind it, a screen to capture whatever came through. He expected that the two slits would produce two bright bars on the screen, the way two windows might cast two stripes of sunlight on a wall. But when Young looked, he did not see two bright stripes. He saw something else. Instead of two simple bands, there was a whole series of alternating light and dark stripes, a pattern of interference, just like ripples in a pond where two waves meet. This was the interference pattern, a signature that could only be created if light behaved as a wave. Where the crests of two waves met, the light was bright. Where a crest met a trough, they cancelled each other, leaving darkness. The conclusion was unavoidable. Light, whatever it was, acted like a wave. For over a century, this wave picture of light held strong. It explained the patterns, the colors, the way light bent and spread. But the universe was not done surprising us. As the 20th century dawned, new experiments began to reveal that light wasn't just a wave. Under certain conditions, it behaved like a stream of particles, discrete packets of energy called photons. The plot thickened when physicists decided to revisit Young's experiment, but this time, instead of light, they would use matter. Electrons, things we had always thought of as solid particles, little billiard balls of reality. When electrons were fired at the double slits, something astonishing happened. The same interference pattern appeared. Particles, individual, solid particles, were somehow acting like waves. The implications were staggering. Matter, like light, seemed to have a dual nature, a wave-particle duality. But the real shock came when scientists decided to slow things down. Instead of firing a stream of electrons, they sent them through one at a time. This way, the electrons would not be able to bump into each other, to interfere in any normal sense. Each electron would be a lone traveler. And yet, the interference pattern still appeared. One by one, Electron impacts built up over time into the same wave-like pattern, as if each particle was somehow interfering with itself, passing through both slits at once in a ghostly superposition of possibilities. This is the point where, if you are not already slightly unsettled, you should be, because it means that a single particle, undisturbed, doesn't seem to take one path or the other. It seems to take every possible path until you look, and that's when the real trouble begins. You see, curious minds wanted to know through which slit does each particle actually go, so they set up a detector, a device to measure the path. The moment they did this, the pattern changed. The beautiful interference fringes vanished, replaced by two simple stripes, exactly as you would expect from little billiard ball particles. The act of measurement, of observation, forced the particle to choose a path, and once it chose, the interference was gone. It was as if the universe had been caught in the act. When unobserved, a particle lives in a cloud of probabilities, taking every route at once, behaving like a wave. But when you watch, it collapses into a single outcome. Wave becomes particle. Possibility becomes fact. Now, here's where our everyday intuition tries to rebel. You might be tempted to think, well, the particle was always going through one slit or the other. We just didn't know which. But the mathematics and the experiments say otherwise. The interference pattern requires that each particle act like a wave passing through both slits simultaneously. The moment you measure which slit it goes through, the wave function collapses, and that behavior is destroyed. This is not a matter of our ignorance, it's a matter of reality itself changing depending on whether it's observed. At first, some physicists thought maybe the measuring device was physically interfering with the particles, disturbing them and ruining the interference pattern. But experiments grew ever more precise, eliminating such possibilities. It didn't matter how gentle or indirect the measurement was. It wasn't about disturbing the particle. It was about the very fact that which path information was available. Let that sink in. Simply knowing the path destroys the wave nature. Information is the key. By the mid-20th century, the double-slit experiment had become the poster child for quantum weirdness. It's been repeated countless times, with electrons, photons, neutrons, even large molecules made of hundreds of atoms. The results are always the same. Observation changes the outcome. But the story doesn't stop there. Because the next logical question, one we'll get to soon, is, what if you decide to look after the particle has already passed the slits? Can your present choice change its past behavior? The answer is, well, let's just say it doesn't make reality any easier to swallow. For now, remember this. The double-slit experiment revealed that particles, when unobserved, behave as if they are everywhere they could possibly be. Only when we look do they decide to be somewhere in particular. It's not just a quirk of light, it's not just a trick of the lab, it is a fundamental truth of the quantum world. And if that's true, then reality as we think we know it may be only one half of the story. The other half, the ghostly unseen half, exists only in the moments before we look. Next, we'll slow things down even further. We'll watch as physicists refine the experiment, stretching time itself into the equation. Because when we choose to observe into the mix, the question of whether particles exist when you're not looking takes a turn into something far stranger and far more unsettling than even Thomas Young could have imagined. The double-slit experiment began as an investigation into the nature of light. It ended up prying open the door to an entirely new reality. But the story didn't stop at beams of photons. Physicists soon asked a deeper question. If light behaves this way, what about matter itself? It's one thing to imagine light as both a wave and a particle. Light feels intangible to us. We can't hold it, weigh it, or keep it in a box. But what about something solid, something with mass? Could the same strange rules possibly apply? The answer came in the form of electrons. These tiny building blocks of atoms, indivisible in classical thought, became the next subjects of the experiment. and the results were enough to shake the foundations of physics. When electrons were fired at the double slits without any attempt to observe which slit they passed through, the familiar interference pattern emerged, peaks and valleys of probability perfectly matching the behavior of waves. Matter, the stuff of the physical world, was showing the same dual nature as light. It didn't just travel from point A to point B like a bullet. It spread out like a ripple across a pond, touching both paths at once. To understand the magnitude of this discovery, remember that electrons have mass, they have charge. In every way we thought we understood, they should act like particles, following predictable trajectories. Yet here they were, behaving like waves of probability. Then came a more daring test. What if we slowed the electron beam until only one electron passed through the slits at a time? In classical terms, this should have destroyed any possibility of interference. Without a second electron to interfere with, each electron should simply leave a single spot on the detection screen, and over time those spots should align into two neat stripes, one behind each slit. That isn't what happened. Each electron, fired alone, still built up the interference pattern. Slowly, one impact at a time, the wave nature revealed itself. It was as if each electron was interfering with itself, somehow passing through both slits at once. The implications were staggering. When unmeasured, the electron didn't exist in one place. It existed in a spread of possibilities, a wave function, until the act of measurement forced it to choose. Here, the idea of reality as a fixed objective thing began to crumble. Because in the quantum realm, the line between possibility and reality is not drawn until the moment of observation. And the unsettling truth is that this isn't just true for light and electrons, it's true for all matter. Experiments have shown interference patterns with neutrons, with whole atoms, even with large molecules made up of hundreds of atoms. The bigger the object, the harder it is to maintain this delicate quantum state, but the principle holds. Unobserved, matter behaves as if it is spread out in space. Observed, it becomes definite. And this leads to an obvious question: why? Why does simply knowing which path the particle took destroy the interference pattern? For a long time, scientists wondered if perhaps the act of measurement physically disturbed the particle, forcing it to behave differently. But modern experiments, using exquisitely gentle detection methods, showed that the disruption wasn't the issue. It was the mere availability of the information. The fact that which path knowledge existed, even if no one actually looked at it, was enough to collapse the wave function. In other words, the universe seems to care not about what you do, but about what you could know. This is a deeply alien way of thinking about reality. We are used to the idea that the physical world is out there, independent of our awareness, obeying its own rules. In the quantum world, the rules appear to change, depending on whether the information about a particle's path is in principle obtainable. If you're thinking that this sounds more like a trick of perception than a law of physics, you're not alone. Many of the greatest minds in science have wrestled with the implications. Einstein famously protested, insisting that the particle must have had a definite position and path all along, whether we measured it or not. But experiment after experiment has failed to reveal such hidden definiteness. What's more, the double-slit setup became a kind of stage for ever more daring variations, each designed to push the mystery further. Could we delay the act of measurement until after the particle had already passed the slits? Could we somehow erase the information after the fact, as if to undo the measurement entirely? These ideas might sound absurd, but they have been tested, and the results have only deepened the mystery. The central lesson so far is this: at the smallest scales, reality resists being pinned down. Particles don't travel a single path like marbles rolling across a table. They move like possibilities, spreading out through space, and only when observed do they crystallize into a definite state. The moment of observation is like the shutter of a camera. It freezes a frame from a film that, until then, was still being written. It's important to note that observation in this context doesn't require a human eye. Any interaction that records which path information counts, a detector, a photon bouncing off the particle, even an environmental disturbance. This is why some physicists prefer the term measurement over observation. It's not about consciousness. It's about whether the universe's bookkeeping system has filed away the data. And yet, despite this clarity, the philosophical overtones remain impossible to ignore. If the universe only chooses a state when the information exists, then in some sense, the act of inquiry shapes reality. It's as if the cosmos is a set of unwritten pages, and only the questions we ask cause the words to appear. By the mid-20th century, the double-slit experiment had become the perfect paradox, simple enough for a student to understand the setup, but deep enough that no one, not even the leading physicists of the age, could agree on what it really meant. Every interpretation of quantum mechanics, from the Copenhagen interpretation to many worlds, has been forced to confront this puzzle. But as strange as the electron's self-interference was, the story was about to get even stranger. Because in the next evolution of the experiment, physicists would tamper not just with the paths the particles could take, but with the very timeline of the measurement itself. And in doing so, they would find hints that choices made in the present might reach back to change what happened in the past. That is where the delayed choice experiments enter the story, and where our grip on cause and effect begins to loosen. We've been using the word observation as though its meaning were obvious, but in quantum mechanics, it's anything but. The word itself carries the scent of human experience, eyes, awareness, intention, and so it's natural to picture a scientist peering into a microscope, catching a particle in the act. But the truth is more mechanical, more impartial, and far stranger. In quantum physics, an observation doesn't require consciousness at all. It doesn't require a human being to bear witness. All it requires is an interaction, an exchange of information that forces a quantum system to make a choice. Here's the problem. In the quantum world, before measurement, a particle doesn't exist in one specific state. It exists in a superposition of all possible states. For an electron going through the double slits, that means it is not simply passing through the left slit or the right slit. It is passing through both. It is also, in a sense, passing through neither. Its existence is smeared across a landscape of possibilities. Then something happens. A detector is placed at the slits. The moment the detector interacts with the particle, perhaps by scattering a photon off it or by registering its position in an electronic circuit, that cloud of possibilities collapses into a single outcome. The particle is suddenly here, not there. It took this slit, not that one. This transformation from uncertainty to definiteness is called wave function collapse. It's the moment the abstract mathematics of quantum probabilities turns into the concrete reality we experience. And in the Copenhagen interpretation, it's the moment reality itself becomes real. But why? Why should an interaction, no matter how gentle, strip away the shimmering web of possibilities and force the particle to commit? The unsettling answer is that we don't truly know. We have a mathematical framework that predicts exactly what will happen when a measurement is made, but it doesn't tell us why this act is special. Why does looking, whether by a human or a machine, cause the wave function to collapse? Why not let the superposition persist? One way to think about it is to borrow an analogy from photography. Imagine you have a camera that's constantly taking long exposure shots. As long as the shutter stays open, the image is a blur. Every position the subject occupies during the exposure is recorded together, smeared across the frame. But the instant the shutter closes, the blur freezes into a single sharp image. In the quantum realm, the shutter is the act of measurement. Before it closes, the particle's wave function contains every possible outcome at once. Measurement freezes it into one. What counts as measurement? Here's the curious part. It doesn't require anyone to actually read the information. It only matters that the information could be known. If a detector captures which slit a particle went through, the interference pattern vanishes, even if the detector's data is deleted before anyone sees it. The mere fact that the path information exists somewhere in the universe forces the collapse. This leads to a profoundly strange conclusion. The universe seems to behave differently depending on whether certain knowledge is in principle obtainable. It's not the act of learning that matters, it's the possibility of learning. You might think this means that observation is just another word for disturbance, that the detector physically bumps the particle in some way, spoiling its wave-like behavior. And in the early days, many physicists thought exactly that. But repeated experiments with increasingly delicate measurement techniques, ones designed to minimize any disturbance, showed the same result. Even the gentlest interaction, one that barely touches the particle, causes the collapse if it extracts which path information. This is why the observer effect is not simply about nudging particles, it's about the very structure of reality. In quantum theory, the world is divided into two regimes: the smooth, deterministic evolution of the wave function when unobserved, and the abrupt probabilistic collapse when observed. Between those two regimes lies a mystery so deep it has been called the measurement problem. Some interpretations, like the many worlds theory, dodge collapse entirely by proposing that all outcomes happen. We just find ourselves in the branch where one specific result occurred. Others, like relational quantum mechanics, suggest that properties don't exist in isolation at all. They only exist in relation to something else. In that view, looking is not about forcing reality to choose. It's about creating a relationship in which certain facts are defined. Still, no matter the interpretation, the double-slit experiment and its variations make one thing clear. When no observation is made, particles behave like waves of probability. When an observation occurs, that delicate superposition collapses into a single definite reality. And somehow the very availability of information is enough to trigger that collapse. If you step back for a moment, you might notice a quiet revolution lurking in this concept. In our everyday lives, we think of reality as existing whether we pay attention or not. A tree in a forest doesn't vanish when we turn our backs. The sun doesn't blink out during the night. But in the quantum world, existence is not so straightforward. A particle's properties may not be definite until something, anything, interacts with it in a way that could, in principle, reveal them. This is not to say that human perception is central to the cosmos. The universe is full of observers that aren't alive: air molecules, stray photons, bits of dust, cosmic rays. Every interaction that records information counts as an observation. In that sense, the quantum world is constantly collapsing into specific outcomes, not because it's conscious, but because it's connected. Yet there is a poetic irony here. While human consciousness isn't required for quantum events to take place, it is our consciousness that notices the paradox. We are the ones troubled by the fact that reality appears to behave differently when watched. The observer effect is not just a feature of the quantum world, it's a mirror, reflecting back our own role as participants in the unfolding of the universe. And the mystery deepens when we change one crucial element: time. What if the decision to observe isn't made until after the particle has already passed through the slits? Can a present choice alter the past? In the next stage of the story, we'll see that quantum mechanics has a habit of answering such questions with a smirk, and an answer that defies common sense. That's where the delayed choice experiments begin. By now, the rules seem strange enough. Unobserved, a particle acts like a wave, passing through both slits at once and creating an interference pattern. Observed, it behaves like a particle, choosing one slit and losing its wave-like signature. It's unsettling, but it feels at least like a sequence. The particle passes the slits, we make a measurement, and the result changes based on whether we measured or not. Cause comes before effect, or so it seems. In 1978, the American physicist John Archibald Wheeler took this setup and added a twist so radical it bordered on the absurd. He called it the delayed choice experiment, and it was designed to ask a question that feels almost like cheating. What happens if we decide whether to observe only after the particle has already passed through the slits? In other words, can our present choice determine what the particle did in the past? Wheeler's idea was elegant in its audacity. Imagine a standard double-slit experiment, but instead of placing detectors at the slits from the start, you wait until the particle is already on its way, perhaps even after it has passed through. At that point, you quickly decide whether to measure which slit it went through or to let it travel unmeasured and interfere with itself. If quantum mechanics works the way many assumed, the decision made after the fact shouldn't matter. The particle's path, you'd think, is already set in stone by the time it's passed the slits. The interference pattern, or lack of one, should be fixed. But when experimentalists put Wheeler's thought experiment to the test, reality refused to play along with classical intuition. If the experimenters chose not to measure the path, even if that choice was made after the particle passed the slits, the interference pattern emerged. If they chose to measure, the pattern vanished, and the results lined up with the particle having chosen one slit or the other. The choice in the present seemed to determine whether the particle had acted like a wave or a particle in the past. This is where quantum mechanics truly begins to feel like a challenge to our deepest intuitions about time and causality. It's tempting to say the particle knew in advance what would be measured, but that doesn't really solve the problem. In the quantum framework, the particle's past behavior doesn't crystallize until the moment the measurement decision is made, even if that moment comes after the particle has passed the critical point. Wheeler himself liked to push the idea further. He imagined a cosmic-scale version of the experiment with a distant quasar emitting a photon billions of years ago. Between us and the quasar lies a massive galaxy, its gravity bending the path of light around it in two different directions, much like two slits. Billions of years after the photon began its journey, we, here on Earth, could choose to set up our detectors in a way that measures which path it took, or not. If we choose to measure, the photon appears to have taken one definite path, all the way from the quasar to our telescope. If we choose not to measure, the photon behaves as though it traveled both paths and interfered with itself, even though that decision was made eons after the photon's journey began. It is as if reality waits for us to make up our minds before committing to a history. In Wheeler's own words, no phenomenon is a phenomenon until it is an observed phenomenon. Of course, this doesn't mean we can go back and rewrite history in the science fiction sense. We can't change a definite past into a different definite past. Instead, quantum mechanics suggests that before measurement, the past is not fixed at all. It exists in a haze of possibilities, and only when an observation is made does one of those possibilities solidify, retroactively giving the illusion of a definite history all along. One way to picture this is to imagine a detective story where the ending hasn't been written yet. The first chapters exist, the characters are set, but the final reveal, the key that makes sense of everything, hasn't been locked in. Depending on which kind of ending you demand, the earlier chapters shift to fit. It's as though the author has been holding multiple drafts and only hands you one when you ask for it, even if your question comes after you've read most of the book. This isn't just philosophical speculation. Laboratory experiments have repeatedly confirmed Wheeler's prediction. Decisions made after a particle should, by any classical reasoning, have already acted, still influence whether the outcome displays wave-like or particle-like behavior. And it gets stranger still. The delayed choice setup has been combined with entanglement experiments where two particles share a quantum connection. In some cases, the decision to observe one particle's properties, made after the other particle has already been measured, seems to retroactively determine the kind of behavior seen in its partner. The quantum links between them stretch across both space and, in a sense, time. The implications are hard to avoid. The quantum world doesn't treat time as the straight one-way street we experience. Past and present blur into a kind of mutual handshake, where the definition of what happened can depend on choices made now. In this view, reality is less a fixed film reel and more a constantly updating story, with the present reaching back to help write the first chapters. Physicists have developed mathematical tools to describe this without invoking magic or science fiction. But the math doesn't make it any less strange. The past we think of as settled is, in the quantum realm, more like wet cement, firm enough to suggest shape, but soft enough to take new impressions when the present presses upon it. And so, the question deepens. If reality can wait for us to decide how it behaved in the past, does that mean it's fundamentally incomplete without our input? Or does it mean the universe already contains all possible histories, and we simply discover which one we're in when we measure? These questions lead directly to the next layer of quantum experimentation, one that takes the delayed choice idea even further. If present choices can seem to affect the past, what happens if we go beyond mere delay and actually erase the record of an observation after it's been made? Could the universe forget what happened and revert to behaving as though the measurement never took place? That is the bizarre premise of the quantum eraser, and it is where the question, "Do particles exist when you're not looking?" takes a turn from strange to truly mind-bending. The delayed choice experiment showed us something unsettling, that reality seems to wait for us to decide how it should have behaved in the past. But quantum mechanics has one more sleight of hand to show us, one that makes the line between past and present blur even further. It's called the quantum eraser, and it asks a question so strange it sounds like the premise of a surreal novel. If the universe records an event, can we erase that record and make it as though the event never happened? To understand the idea, we have to go back to the double-slit experiment. Remember, when no which path information is available, we get an interference pattern. When we measure which slit the particle goes through, the interference pattern disappears, the wave function collapses, and the particle behaves as though it chose a single slit. The quantum eraser takes this one step further. It says, what if we measure the path, but then remove or scramble that information before we look at it? Could we restore the interference pattern after the fact? Could we make reality forget it had ever been measured? In 1982, physicists Yoon-Ho Kim, R.U., S.P. Kulik, Y. Shi, and Marlon O. Scully devised a way to test this. The setup is more complex, but the essence is elegant. It starts with entangled photons, pairs of particles linked so that what happens to one instantly correlates with the other. One photon, call it the signal photon, heads toward the double slits. The other, the idler photon, takes a different path, eventually reaching a set of detectors that can reveal or hide which slit the signal photon passed through. Here's the trick. The choice to reveal or hide the path is made for the idler photon after the signal photon has already hit the screen. The two photons are separated in space, and the erase decision happens later in time, but because they are entangled, the information about the path is shared between them. When the which path information from the idler is preserved, the signal photon's data shows no interference pattern, as though it went through one slit or the other. But when that which path information is erased, by scrambling it so it can't even in principle be known, the interference pattern reappears in the signal photon's data. This happens even if the erase decision is made after the signal photon has already been detected. The interference or non-interference is only revealed later, when the results from the two photons are compared. This is where the language gets poetic, because it's hard to avoid anthropomorphizing reality. It's as if the universe kept its options open, and when we removed the possibility of knowing the path, it quietly reverted to wave-like behavior, as though the measurement had never been made. It's not that the particle changed its mind in a conscious sense. Rather, quantum mechanics tells us the outcome wasn't fixed until all the information that could define it was settled. What's even stranger is that this erasing isn't like burning a photograph. The act of erasure doesn't remove the event from existence, it changes the set of correlations we can observe. Without which-path information, the mathematical description of the system still allows for interference. With it, interference is impossible. This suggests a kind of bookkeeping that's built into the fabric of reality. It's as if the universe keeps track of every interaction, but whether those interactions affect what we see depends on whether their records can, even in principle, be reconstructed. The philosophical implications are dizzying. The quantum eraser seems to confirm that it's not the act of looking that changes things, but the existence of the possibility of knowing. If that possibility is destroyed, the universe behaves as though the knowledge never existed, even retroactively. It's tempting to imagine this as a kind of cosmic undo button. Press it, and the particle's history shifts back into superposition. But the deeper truth may be that history in the quantum world isn't a single rigid line. It's a network of possibilities, and those possibilities only collapse into specific events when all the relevant information is fixed. For those who want to avoid any whiff of the mystical, the quantum eraser is still strange enough on its own terms. The effect doesn't require human consciousness, intention, or awareness, only the manipulation of information. The decision to keep or erase which-path data can be made by a random number generator, or even by natural processes. The result is the same. Information available equals no interference. Information erased equals interference. This pushes the question, do particles exist when you're not looking, into a more refined, more dangerous form. Maybe it's not about looking at all. Maybe it's about whether reality has committed to a specific version of events. If the record is erased, perhaps reality itself reverts to uncertainty. Physicist Marlon Scully once described it as turning the past into the future, because what we think of as past events in quantum mechanics often remain undetermined until later choices lock them in. The quantum eraser experiments make this locking-in process visible in a way that few other experiments do. And it's worth noting, these ideas aren't confined to exotic lab setups. In principle, the same rules govern the entire universe. The cosmic microwave background, the scattering of photons in deep space, the collisions of particles in your own body. All of these are shaped by the same interplay between possibility and information. If there is no record, the past may remain in a quantum limbo. At this point in our journey, we've seen that quantum experiments can toy with reality in unsettling ways. We can delay the decision to measure and affect what happened earlier. We can erase the record of a measurement and restore wave-like behavior after the fact. And in all of this, the question of what's real when we're not looking becomes harder to answer. The interpretations of these results vary wildly. Some say the particle always had a definite state, and we're just uncovering correlations we didn't notice before. Others argue that the particle truly has no definite state until measured, and the erasure removes the constraints that force it into one. And then there are those who see this as evidence that the wave function is the real physical entity, and that our interventions change its shape in time, as well as in space. Whatever the interpretation, the quantum eraser leaves us with a haunting image, reality, half-written, waiting to see whether the ink will dry or whether the page will be wiped clean and left blank again. And now we arrive at the point where these experimental puzzles begin to collide with the great theoretical frameworks, the interpretations of quantum mechanics that try, each in their own way, to make sense of what's going on. The first of these, and still one of the most influential, is the Copenhagen interpretation, the idea that reality doesn't take shape until the moment of measurement. By the time the quantum eraser experiments entered the conversation, the scientific world had already been wrestling with these mysteries for decades. And the interpretation that had dominated since the early days of quantum theory, the one taught to generations of physicists as the standard view, was the Copenhagen interpretation. Its roots stretch back to the 1920s in the bustling intellectual atmosphere of Copenhagen, Denmark, where Niels Bohr, Werner Heisenberg and their colleagues were trying to make sense of the brand new, deeply unsettling quantum equations. These equations worked beautifully. They could predict the results of experiments with incredible precision, but what they meant about reality was far less clear. The Copenhagen interpretation took a pragmatic stance. The wave function, that strange mathematical object representing all possible states of a particle, doesn't describe an underlying physical reality in the way we might expect. Instead, it encodes probabilities, a catalogue of possible outcomes. And here's the crucial part. Those probabilities remain possibilities until a measurement is made. At that moment, the wave function collapses into one specific outcome. In other words, before measurement, the particle doesn't have a definite position, momentum, or path. These properties simply do not exist as facts. They exist only as probabilities, only as potentialities. When we measure, we force nature to choose, and the particle becomes something definite. Bohr famously argued that asking what a particle is doing when we're not observing it is meaningless. Physics, in his view, isn't about uncovering some hidden objective reality. It's about describing the outcomes of measurements. The act of measurement isn't just revealing reality, it's creating it. This is a radically different way of thinking about the world. In classical physics, objects have properties whether or not we measure them. A planet has a position in its orbit whether or not we're looking through a telescope. A coin lying under a cup is either heads or tails even before we lift the cup. In the Copenhagen view, quantum objects are not like that. Until you lift the cup, until you measure, they exist in a state of superposition, neither this nor that, but somehow both and neither at once. This brings us back to the question at the heart of our journey. Do particles exist when you're not looking? The Copenhagen answer is, in a sense, not in the way you think. Unmeasured, they do not have definite properties at all. One of the most famous and infamous illustrations of this is Schrödinger's cat, a thought experiment designed to show just how absurd this could sound when scaled up. In Schrödinger's scenario, a cat inside a sealed box is linked to a quantum event, say the decay of a radioactive atom that has a 50% chance of occurring in an hour. If the atom decays, poison is released and the cat dies. If it doesn't, the cat lives. According to the Copenhagen interpretation, until someone opens the box and looks inside, the atom is in a superposition of decayed and not decayed, and so the cat is in a superposition of alive and dead. Only observation forces the system into one definite state. Bohr didn't mean to suggest that macroscopic cats are actually flitting between life and death in any physical sense. His point was that the quantum description doesn't provide us with a definite reality until we measure it. The line between the quantum world and the classical world, between superposition and definiteness, was, in his view, simply where the measuring apparatus and ultimately the observer comes into play. Einstein found this deeply unsatisfying. His retort, "Do you really believe the moon isn't there when you're not looking at it?" captured his discomfort. To him, physics should describe an objective reality that exists independently of observers. The idea that reality is undefined until observed was, in his eyes, an abdication of physics' deeper mission. But Bohr held his ground. He argued that the job of physics was not to describe what reality is in some hidden metaphysical sense, but to predict what we will observe when we interact with it. Asking what's really happening between observations was, in his words, an unanswerable, and therefore meaningless, question. For decades, the Copenhagen interpretation wasn't just the dominant view, it was, in many quarters, the only acceptable view. It allowed physicists to sidestep the thorny metaphysical debates and focus on doing the calculations that worked. It was pragmatic, efficient, and, some would say, evasive. Critics of Copenhagen point out that it never really explains how or why the wave function collapses. It just says that it does when measurement happens. What counts as a measurement? Is it any interaction with a macroscopic system? Is it any irreversible recording of information? Is it the involvement of a conscious observer? Bohr was careful not to pin down an exact definition, perhaps because any such definition risked exposing just how fuzzy the boundary really is.
Still, the Copenhagen interpretation has one major strength. It aligns perfectly with what we actually see in experiments. When we don't measure which path a particle takes, we get interference. When we do measure, we don't. The wave function is an elegant mathematical tool that predicts this behavior flawlessly. If you're willing to live with the idea that reality between measurements is undefined, Copenhagen works just fine.
And that's the subtle brilliance and the haunting discomfort of the Copenhagen view. It doesn't say particles vanish when you're not looking. It says that definite properties vanish. What remains in their place is a cloud of potentialities, a mathematical description of what could be, waiting for measurement to make it so. But for those like Einstein, this was not enough. They believed that beneath the strange dance of probabilities, there must be a deeper, hidden structure, one where particles do have definite properties at all times, even if we can't see them. That conviction would lead to one of the most famous scientific debates in history, Einstein versus Bohr, in a battle over whether God really does play dice with the universe. The Copenhagen interpretation may have been the dominant view, but not everyone was willing to accept it. Albert Einstein, one of the founders of quantum theory itself, was perhaps its most relentless critic. For him, the idea that particles had no definite properties until observed was not just puzzling, it was unacceptable. Physics, he believed, should describe a reality that exists whether or not anyone is looking. Einstein respected Bohr's intellect. He even admired the elegance of the mathematics behind quantum mechanics, but he could not accept the philosophical implications. To him, the Copenhagen interpretation was incomplete. It described what we see, but not what is. His objection is summed up in the line he's most famously associated with in this debate: God does not play dice with the universe. This wasn't a theological statement. Einstein wasn't invoking a deity in the literal sense. God was his metaphor for the fundamental order of the cosmos. He believed the universe operates according to precise, deterministic laws. Randomness, in his view, was just a placeholder for ignorance, a sign that our theory was missing some hidden layer of reality. Bohr, in turn, pushed back with equal force. In his mind, Einstein's insistence on an underlying deterministic reality was an attachment to classical thinking, an unwillingness to embrace the radical nature of the quantum world. Bohr famously replied, "Einstein, stop telling God what to do." The clash between these two giants was as much about worldview as about physics. For Einstein, physics without realism, without a belief in an objective reality, was unmoored. For Bohr, physics without acceptance of quantum uncertainty was a refusal to confront what experiments were telling us. Einstein didn't just object in words. He tried to prove that quantum mechanics was incomplete through thought experiments designed to expose contradictions in the Copenhagen view. One of the earliest and most famous came in 1935, when he, along with Boris Podolsky and Nathan Rosen, published what became known as the EPR paradox. The EPR paper presented a simple, powerful argument. Suppose two particles interact and then fly apart in opposite directions. According to quantum mechanics, certain properties of these particles, like their spins or momenta, are correlated. If you measure one particle's property, you instantly know the others, no matter how far apart they are. Now, in the Copenhagen interpretation, before measurement, neither particle has a definite value for that property. Only the act of measuring one collapses its state, and, mysteriously, the other particle's state collapses too, even across vast distances. To Einstein, this spooky action at a distance was absurd. If the measurement of one particle could instantly affect the other, that would seem to violate the principle that nothing can travel faster than light. The only reasonable explanation, he argued, was that the particles already had definite values all along, determined when they first interacted. We just didn't know them until we measured. Quantum mechanics, in his view, must therefore be incomplete, missing the hidden variables that encoded those properties. Bohr's response was sharp and unwavering. He argued that Einstein was clinging to an outdated notion of separability, the idea that distant objects must have independent realities. Quantum mechanics, Bohr said, showed that entangled particles are not separate systems at all. They are part of a single unified quantum state. The measurement doesn't send a signal to the other particle. It reveals a property that belongs to the pair as a whole. For years, the debate between Einstein and Bohr continued, in letters, in conferences, and in famously heated discussions. Each man brought a unique blend of scientific rigor and philosophical conviction. Einstein could craft thought experiments that exposed what he saw as the absurdities of Copenhagen. Bohr could deconstruct those same thought experiments, showing how they fit perfectly within quantum mechanics once you abandoned classical intuitions. What made the argument so enduring was that it wasn't simply about the technical details of physics. It was about the nature of reality itself. Was the universe fundamentally deterministic, with quantum randomness hiding deeper laws we hadn't yet discovered? Or was indeterminacy baked into the fabric of reality, an inescapable feature of the quantum world? For decades, it seemed the debate might remain purely philosophical. Quantum mechanics worked so well in practice that many physicists chose Bohr's pragmatic path: shut up and calculate. The predictions matched experiments, so why fret about the underlying reality? But Einstein's challenge didn't fade. His insistence that quantum mechanics might be incomplete planted the seeds for future tests that could, in principle, determine whether hidden variables were possible. That seed would eventually grow into the work of physicist John Bell in the 1960s, and the experiments in the 1970s and 80s that would test Bell's ideas. In those future tests lay the possibility of settling at least part of the Einstein-Bohr argument. If hidden variables existed and were local, meaning they couldn't influence each other faster than light, then certain inequalities in measurement results should always hold. If experiments violated those inequalities, it would mean that no local hidden variable theory could explain quantum mechanics. Bohr did not live to see those experiments, and neither did Einstein. But when they finally came, the results would force the physics community to confront a reality stranger than either man had perhaps fully anticipated. Einstein wanted a universe that was orderly, deterministic, and local, one where particles had properties independent of observation. Bohr embraced a universe where outcomes were only probabilities until measured, where reality itself was dependent on the experimental context. The experiments inspired by their debate would show that if there is a deeper reality beneath quantum mechanics, it cannot be both local and classical in the way Einstein had hoped. The universe, it seems, plays by rules more alien than either side of the argument might have been fully prepared for. The clash between Einstein and Bohr remains one of the most famous intellectual rivalries in science, not because one was clearly right and the other wrong, but because their disagreement illuminated just how far quantum mechanics pushes us from common sense. In their debates, we see two different ways of grappling with mystery, one seeking hidden order, the other accepting uncertainty as fundamental. And in the next chapter of this story, the chapter written after both men were gone, we'll see how John Bell took their philosophical duel and turned it into an experimental challenge. A test that would, once and for all, show whether Einstein's God truly refused to play dice, or whether the dice were not only rolling, but rolling in a way no local theory could ever explain. When Einstein and Bohr debated the meaning of quantum mechanics, their arguments often circled back to one question: could there be hidden variables, unseen elements of reality that determined the outcomes of quantum events, restoring an objective, definite world behind the apparent randomness? Einstein's answer was yes. Bohr's was number. For decades, the argument seemed philosophical, a battle of interpretation rather than prediction. But in 1964, an Irish physicist named John Bell changed the game. He found a way to turn this philosophical divide into something testable. Bell's breakthrough was deceptively simple in its premise. If hidden variables exist and if they obey the principle of locality, meaning no influence can travel faster than light, then certain statistical patterns must appear when we measure entangled particles. Those patterns are described by mathematical inequalities, now known as Bell inequalities. If quantum mechanics is right, and there are no local hidden variables, these inequalities should be violated. If Einstein's view is right, if particles carry predetermined properties independent of observation, the inequalities should always hold. In Bell's hands, what had been a thought experiment became a clear experimental challenge. Set up a test with entangled particles, measure their correlations, and see which prediction the universe chooses. Here's the setup. Imagine two particles born together in an entangled state. For example, two photons emitted from a single source, their polarizations linked. They fly apart in opposite directions, potentially light years away from each other. You measure the polarization of one photon at a chosen angle, and your colleague measures the polarization of the other photon at a different angle. In a local hidden variable world, the correlations between your results are limited. They can't be stronger than what's allowed by classical statistics. In quantum mechanics, however, the correlations can be stronger in a way that blatantly violates Bell's inequality. Bell's theorem didn't tell us which answer was correct. It gave us a tool to find out. But there was a catch. Performing the experiment with the necessary precision wasn't easy in the 1960s. It would take nearly 2 decades before technology caught up. That moment came in the early 1980s when physicist Alain Aspect and his team in France carried out a landmark series of experiments with entangled photons. They set up detectors at different orientations, rapidly switching the measurement settings while the photons were already in flight. The results were clear. The correlations between the photons violated Bell's inequalities. The implications were staggering. If the experiments were correct, and they've since been repeated and refined many times, then local hidden variables cannot explain quantum mechanics. Either hidden variables don't exist at all, or they do, but they allow for non-locality, influences that leap across space instantly, as if distance didn't exist. For Einstein, this was a bitter pill. His spooky action at a distance, the phenomenon he introduced as a criticism, turned out to be real. Entangled particles behave as if they are parts of a single system, no matter how far apart they are, and measurement outcomes on one side seem to correlate instantly with outcomes on the other. To be clear, this doesn't mean faster-than-light communication is possible. The correlations are real, but they can't be used to send information in a way that would violate relativity. What it does mean is that the quantum world does not respect locality in the classical sense. The idea that each particle has its own independent reality, unaffected by distant events, collapses under the weight of the data. Bell's work and Aspect's experiments closed the gap between philosophy and physics. They told us something concrete about the nature of reality. If there is an underlying reality beneath quantum mechanics, it cannot be both local and realistic in the classical sense. You can have one, but not both. And quantum mechanics forces us to give up locality, or to give up the idea that properties exist before we measure them. This finding aligns uncomfortably well with Bohr's view. In the Copenhagen interpretation, properties like polarization, spin, or position don't exist in a definite form until they're measured. Between measurements, they exist only as probabilities. Entanglement means that when one particle's property becomes definite, the other's does too, instantly, even across vast distances. For some, Bell's theorem is the nail in the coffin for Einstein's hope of a tidy local reality, but others see it as pointing toward even deeper mysteries. If locality fails, perhaps the universe is fundamentally interconnected at a level beyond space and time. Perhaps space itself is not the ultimate stage on which reality plays out, but rather an emergent structure born from something more fundamental. Bell himself was careful. He didn't claim to have answered every question about reality. Instead, he gave us a sharp boundary between what's possible and what's not. In doing so, he pushed quantum mechanics into territory where our classical intuitions simply don't apply. The world is either non-local, or reality as we understand it doesn't exist until we measure it. Either way, the dream of a neat, deterministic universe that simply ticks along like a clock, the dream Einstein cherished, does not survive. Over the years, experiments have grown ever more sophisticated. Loopholes, subtle ways the results might be explained without abandoning locality or realism, have been closed one by one. By 2015, multiple loophole-free Bell tests confirmed the violation of Bell inequalities beyond reasonable doubt. The verdict of nature appears to be clear. The quantum world is non-local in some form, and any hidden variables that exist must operate outside the familiar framework of space and time. This brings us to a fork in the road. Some interpretations, like Copenhagen, accept the loss of locality and embrace the probabilistic nature of reality. Others, like the many worlds interpretation, avoid wave function collapse entirely at the cost of imagining a constantly branching multiverse, and still others propose radical alternatives such as pilot wave theory, in which particles have definite properties guided by a non-local pilot wave. But no matter which path you take, Bell's theorem is a signpost that can't be ignored. It tells us that the quantum world doesn't just challenge our intuitions, it overturns them. The connections between entangled particles are real, instantaneous, and immune to distance in a way no classical picture can account for. In the end, Bell didn't just test Einstein's doubts, he reframed them. The question is no longer whether God plays dice. It's whether the dice are being thrown in a place where our ordinary notions of space, time, and causality even make sense. And that in turn opens the door to one of the most radical proposals in all of physics. What if the wave function never collapses at all? What if every possible outcome of a quantum event actually happens, just not all in the same universe? That's the idea behind the many worlds interpretation, and it changes the question, do particles exist when you're not looking, into something far stranger. Not only do they exist, but so do all the versions of them, and you, that you never get to see. By the mid-20th century, physicists were in agreement about one thing: quantum mechanics works. Its predictions match experiments with uncanny precision. But why it works, what it says about the nature of reality, was still a battlefield. The Copenhagen interpretation had ruled for decades, accepting that particles exist in superposition until measured, and that measurement forces the wave function to collapse into a single outcome. But in 1957, a young physicist named Hugh Everett III offered a radically different answer. What if the wave function never collapses at all? Everett's idea was disarmingly simple and explosively profound. The mathematics of quantum mechanics, he pointed out, describes a wave function that evolves smoothly and deterministically over time. The idea of collapse, an abrupt probabilistic jump from many possibilities to one, wasn't in the equations themselves. Collapse was something physicists had added to explain why we see definite results. But maybe that extra step wasn't needed. Instead, Everett proposed when a quantum measurement happens, the universe doesn't choose one outcome and discard the others. It keeps them all. Every possible result of the measurement happens, each in its own branch of reality. If an electron could be spin up or spin down, the universe splits into two versions. One where it's spin up and another where it's spin down. Both are equally real. Both continue forward in time. And both contain a version of you, observing that outcome. In Everett's view, the wave function never collapses. It just keeps evolving, and the branching never stops. Every quantum event with multiple possible outcomes sends the universe into multiple parallel versions, each as real as the one you experience. You only perceive one branch because you, and your memories, are part of that branch. The other versions of you, in the other branches, perceive their outcomes with equal certainty. This interpretation became known as the Many Worlds Interpretation, MWI. At first, it was ignored or dismissed as science fiction. The idea of an ever-splitting multiverse sounded absurd. How could such an extravagant picture of reality be necessary just to explain why a particle acts like a wave until measured? But Many Worlds has an elegance that's hard to deny. It removes the need for a mysterious, ill-defined collapse. It treats the wave function as real, not just a mathematical tool. And it keeps quantum mechanics purely deterministic. The probabilities we calculate are simply the proportions of branches in which each outcome occurs. From this perspective, the question, do particles exist when you're not looking, changes entirely. In MWI, particles always exist in definite states within each branch. When you're not looking, they're still there, in every possible configuration allowed by the wave function. You just don't see most of those configurations because you're not in those branches. Take the double-slit experiment. In the Copenhagen view, an unobserved particle is in a superposition, behaving like a wave until measurement collapses it to a single path. In Many Worlds, the particle always goes through both slits, but in different branches of the universe. When you measure which slit it went through, you're not collapsing the wave function. You're entangling yourself with the outcome. In one branch, you see it go through the left slit. In another, you see it go through the right. Each branch contains a consistent reality where the result makes perfect sense. It's important to note that Many Worlds doesn't mean new universes are being created out of nothing at each split. In the mathematics, all the branches exist together in a single vast wave function, the universal wave function. The splitting is not an explosion of new realities, but a continual unfolding of what's already implicit in the quantum description. The cost of this elegance is philosophical vertigo. If MWI is true, there are countless versions of you, some only a moment old, others diverged from your life decades ago, living out every possibility that quantum mechanics allows. In some branches, you made a different choice this morning. In others, events took wildly different turns. And in most of them, you'll never know those other versions exist. Critics of Many Worlds often point to its lack of direct experimental confirmation. The theory predicts the same measurable results as Copenhagen for any experiment we can do. Its differences are philosophical and ontological. It describes a radically different underlying reality without changing the numbers. For some physicists, that makes it less of a theory and more of an interpretation. But supporters argue that Many Worlds is the simplest, cleanest way to make sense of quantum mechanics without adding ad hoc rules like collapse. The multiverse may sound extravagant, they say, but it's really just taking the math seriously. There's also an intriguing connection between Many Worlds and the phenomena we've already explored, like delayed choice and quantum erasers. In the MWI picture, the retroactive changes we see in those experiments are not reality rewriting itself. They're the result of branching and entanglement playing out in a way that makes each branch's history consistent within itself. The wave function's evolution is smooth and unbroken. It's only our experience locked into a single branch that makes it look like the past changed. And what of Bell's theorem and the apparent non-locality of quantum mechanics? In Many Worlds, there's no faster-than-light communication between particles. Instead, entanglement correlations arise because the particles and the observers are part of the same branch of the universal wave function. When a measurement happens, the branching locks in the correlations across both locations, no matter how far apart they are. For those willing to accept its implications, Many Worlds offers a reality that is deterministic, consistent, and free of mysterious collapses. But it comes with a staggering price, an infinite tapestry of parallel versions of everything, each as real as the one you inhabit. Your life is just one thread among countless others, each weaving its own coherent story. The interpretation also reframes the role of the observer. In Copenhagen, observation plays a special role in creating definite reality. In many worlds, observation is just another quantum interaction, one that entangles the observer with the system. You don't create reality by looking, you split into versions that see different realities. For some, this is liberating. For others, it's unsettling to think that every possibility happens somewhere, and that you are not a singular, unique entity, but part of a vast, branching continuum. But in either case, it challenges the way we think about existence itself. In many worlds, the universe doesn't need you to look to decide what's real. Everything that can happen does happen, somewhere. The question is not whether particles exist when you're not looking, but how many versions of them, and of you, are out there, unseen. And while many worlds offers one possible escape from the mystery of wave function collapse, it's not the only contender. Another approach, very different in spirit, suggests that reality is not a fixed backdrop at all, but something that exists only in relationships between systems. It's called relational quantum mechanics, and it paints a picture of reality as a web of interactions with no absolute state at all. If many worlds is a sweeping, multiverse-spanning vision of quantum reality, relational quantum mechanics, or RQM, is something more intimate. Where Everett's interpretation says everything exists in a vast, branching totality, RQM takes a quieter, almost minimalist view. Perhaps there is no single, absolute reality at all. Perhaps reality is nothing more and nothing less than the relationships between things. The idea emerged in the 1990s, championed by Italian physicist Carlo Rovelli. His proposal was as simple as it was radical. The properties of a system, like a particle's position, spin, or momentum, don't exist as standalone facts. They only exist relative to another system. Think of it like a conversation. Words have meaning only in relation to the person hearing them. Outside of that relationship, the words are just vibrations in the air. In RQM, quantum properties are like those words. They are only meaningful in the context of an interaction between two systems. This immediately reframes our central question: do particles exist when you're not looking? In a way that sidesteps the need for wave function collapse or branching universes. The answer becomes, a particle has no absolute properties at all unless it is in relation to something else. When we're not looking, when there is no interaction, the particle simply does not have a definite value for the property in question. In this view, observation is just one kind of interaction. Two particles scattering off each other, a photon hitting an atom, a detector registering a click. All of these are relationships that give rise to definite facts relative to each participant. You might measure a particle and see it spin up. Relative to you, that is now a fact. But relative to some other system that hasn't interacted with it yet, the particle may still be in a superposition. This is where RQM gets tricky for our classical intuition. We're used to thinking that facts are universal. If the book is on the table, it's on the table for everyone. But in RQM, quantum facts are perspectival. What's true for one observer may not be true for another until they interact and share information. Rovelli often uses the analogy of Einstein's relativity, where space and time are not absolute but depend on the observer's motion. Just as there's no single now that all observers agree on, there's no single set of quantum properties that all observers agree on until they interact. Reality is a network of overlapping perspectives, stitched together through interaction.
Now, this doesn't mean anything goes, or that reality is subjective in the everyday sense. The relational view is still grounded in rigorous quantum mechanics. The equations work exactly the same way. What changes is the interpretation of what those equations describe. In RQM, the wave function is not a picture of an objective state of the world, but a tool for calculating the probabilities of outcomes relative to a particular observer.
The double-slit experiment looks different through this lens. An unmeasured particle doesn't exist in some mystical half-real state. Rather, its path is simply undefined relative to the measuring apparatus until an interaction occurs. Once the interaction happens, the particle's behavior becomes a definite fact for that apparatus. But for another system that hasn't interacted with it yet, the fact might still be undefined. This relativity of facts also offers a new way to think about the famous paradoxes of quantum mechanics. Take Wigner's friend, for example. In this thought experiment, Wigner's friend is inside a lab performing a measurement on a quantum system. Relative to the friend, the system's wave function has collapsed to a definite outcome, but for Wigner, who hasn't opened the lab door yet, the entire lab, including the friend, is still in a superposition. In the Copenhagen view, this creates a problem. When exactly does collapse happen, and for whom? In many worlds, both outcomes happen in different branches, but in RQM, there's no contradiction at all. The result is definite relative to the friend and indefinite relative to Wigner until they interact and compare notes. Reality is not a single shared ledger of facts. It's a web of perspectives that synchronize only when connected. One of the strengths of RQM is that it avoids some of the more extravagant implications of other interpretations. There's no need for infinite branching universes, and no need for a special collapse triggered by consciousness or measurement. There's also no conflict with Bell's theorem, because the correlations seen in entanglement are simply relationships that manifest when two systems interact, not instantaneous influences traveling across space. However, the relational approach comes at a philosophical cost. It challenges our deep-seated belief in a single, observer-independent reality. It asks us to accept that what is real for one observer may not yet be real for another, and that reality in the quantum world is not a God's-eye view of everything at once, but a patchwork of interlocking relationships. If this sounds strange, remember that we already accept something similar in other areas of physics. In relativity, different observers can disagree on the order of events, the length of a moving object, or the duration of a trip, and all of them can be correct from their own frames of reference. RQM extends that idea into the quantum realm. Different observers can disagree about the state of a system, and all can be correct relative to themselves. This way of thinking brings a certain clarity to our central question. Do particles exist when you're not looking? In RQM, they exist, but not in the way we imagine. They don't carry a pre-packaged set of definite properties waiting to be revealed. Instead, those properties emerge only in relation to other systems. Without a relationship, there is no fact to speak of, not because the particle is unreal, but because the question of its state is meaningless outside of a context. In a way, RQM shifts the mystery from "how does reality decide what's real?" to "why should we expect reality to have absolute facts in the first place?" It invites us to think less about isolated objects and more about the connections between them. Reality in this picture is not made of things. It is made of interactions. From here, our exploration moves toward the most contentious territory of all, the idea that observation might involve not just physical interaction, but consciousness. Some interpretations tiptoe toward this idea cautiously, others embrace it directly. It's a path that has divided physicists for decades because, while consciousness is undeniably real to us, its place in the machinery of the universe is anything but clear. Next, we'll step into that controversial ground, the notion that the mind itself might play a role in deciding what becomes real. We've explored interpretations that keep the observer strictly in the realm of physics, an observer being any system that interacts, any process that records information. In those views, the role of a human mind is no different than that of a photon bouncing off a dust mote. But there is another, far more contentious thread in the history of quantum mechanics, one that suggests consciousness itself might be central to the measurement process. It is a path strewn with philosophical landmines, scientific skepticism, and the occasional foray into mysticism. And yet, it refuses to disappear entirely from the conversation. The seeds of this idea were planted in the early 20th century, when pioneers like John von Neumann examined the so-called measurement problem. The question of when and how the wave function collapses from many possibilities into one definite outcome. In von Neumann's analysis, you could imagine a chain of measurements. The particle interacts with a detector, the detector sends a signal to an instrument, the instrument records a reading, and finally a person looks at the reading. At which point in that chain does the collapse occur? If every device in the chain is itself a quantum system, it could, in principle, be described by a larger wave function, entangled with the particle. This leads to a disturbing conclusion. Unless you stop the chain somewhere, the superposition just keeps growing, incorporating more and more of the measuring apparatus, even theoretically the human observer. Von Neumann suggested that the chain might end only when the result enters the mind of a conscious observer. Consciousness, in this view, is not just another physical process. It's something fundamentally different, something that cannot be described by the equations of quantum mechanics. When the mind becomes aware of the result, the wave function collapses. This is a provocative claim, and most physicists today are deeply wary of it. But it gained some traction in the mid-20th century, particularly with physicist Eugene Wigner. Wigner famously proposed the thought experiment known as Wigner's friend, which we touched on earlier. In it, Wigner's friend performs a quantum measurement inside a sealed lab, seeing a definite outcome. From the friend's perspective, the wave function has collapsed. But for Wigner, outside the lab and unaware of the result, the entire lab, friend included, could still be in a superposition. If collapse only occurs when a conscious mind observes the result, whose mind counts? The friend's? Wigner's? Does the universe remain in superposition until someone, perhaps any conscious being, becomes aware? Wigner later retreated from the strong version of this idea, acknowledging that it raised more questions than it answered. But the association between consciousness and collapse lingered, fueled in part by the difficulty of defining measurement in purely physical terms. One reason this notion is so divisive is that consciousness is itself a deep mystery. Neuroscience can trace brain activity, map neural networks, and correlate patterns with thoughts and sensations. But the subjective quality of awareness, the experience of seeing, hearing, or knowing something, remains unexplained. To many physicists, it feels premature to place consciousness at the foundation of physics when we don't even fully understand it biologically, and yet there's an undeniable appeal to the idea. Quantum mechanics already tells us that the act of observation changes the behavior of particles. It's a short leap, perhaps too short, to wonder whether the special kind of observation that conscious beings perform is the key. After all, when we talk about measurement in everyday life, we almost always mean a measurement made by someone.
This view has inspired more than a few bold and often controversial speculations. Some have suggested that the universe itself might be akin to a vast quantum computer, with consciousness serving as the final readout that fixes reality. Others see in it a bridge between physics and philosophy, or even physics and spirituality.
The danger, of course, is that it's easy to drift from science into unfalsifiable territory. Without a clear, testable mechanism linking consciousness to collapse, the idea becomes a matter of personal belief rather than empirical inquiry. For many working physicists, that's where the line must be drawn. Still, there have been serious attempts to explore whether consciousness could play a measurable role. Some experiments have tested whether human attention or intention can influence quantum systems, often using random number generators or variations of the double-slit experiment. The results have been inconclusive and, in many cases, heavily criticized for lack of rigor. The evidence so far does not support a direct causal link between human awareness and quantum outcomes. But even without experimental proof, the idea serves as a useful philosophical probe. It forces us to confront the fact that the boundary between the quantum and classical worlds, between the indefinite and the definite, is not clearly marked. If we reject consciousness as the key, we must explain collapse in some other way. If we accept it, we must grapple with why consciousness should be different from any other physical process. For our central question, do particles exist when you're not looking? The consciousness-based view gives a striking answer. Particles do not take on definite properties until a conscious observer becomes aware of them. Without an observer, the world remains in a kind of liminal state, a haze of probabilities awaiting the clarifying light of awareness. Most physicists would caution that this is not the mainstream view. It is a speculative interpretation, one that sits on the fringes of the quantum debate. But it has had an enduring influence on popular imagination, in part because it gives human beings a starring role in the cosmic drama. If it's true, then reality as we know it depends, quite literally, on our presence. Yet physics does not need consciousness to make quantum mechanics work. And there are other ways to reconcile the observer effect without making the mind a special case. One of those ways is to zoom out, far out, and ask whether the universe itself might be the ultimate observer. Could the cosmos be constantly measuring itself through its own interactions, so that particles and galaxies alike exist in definite states even without us? That question takes us from the inner theater of the mind to the vast stage of the universe, and it's where we turn next. Up to now, we've been focused on observers in the traditional sense, people, detectors, measuring devices, any system capable of interacting with and recording information about another. But what happens when we lift our gaze from the laboratory to the cosmos itself? Could it be that the universe doesn't need us to look because it is already looking at itself? To explore this idea, we have to remember a key fact about the quantum world. The line between observer and system is not fixed. Any interaction that leaves a trace, any exchange of information, counts as a measurement. And the universe is full of such interactions, from the scattering of photons to the gravitational bending of light. Consider the cosmic microwave background radiation, the faint afterglow of the Big Bang, still bathing the cosmos nearly 14 billion years later. Those ancient photons have been bouncing off matter since the universe's earliest moments. Every collision, every deflection, every absorption is an interaction that forces a quantum system into a definite state relative to its environment. In effect, the universe has been conducting its own measurements since the beginning. This idea is central to what's called decoherence theory. Decoherence doesn't require a conscious observer to collapse the wave function. Instead, it says that as soon as a quantum system interacts with its environment, exchanging even the tiniest bit of information, its delicate superposition becomes entangled with so many degrees of freedom that interference becomes impossible. The environment measures the system simply by existing around it. In this picture, the universe is constantly observing itself through the ceaseless web of interactions between particles, fields, and forces. Every photon that bounces off a grain of dust, every atom that collides with another, every gravitational tug between distant stars, all of these are measurements in the quantum sense. The result is that, on macroscopic scales, we see a stable, classical world, not because we're looking at it, but because the environment is looking at everything all the time. But here's where things get subtle. Decoherence explains why we don't see large objects in superpositions, why the moon doesn't appear smeared across the sky when we're not looking. Yet decoherence alone doesn't answer the deeper ontological question. Does this process create definite outcomes, or does it simply make the alternatives inaccessible to us? Some interpretations, like many worlds, say decoherence doesn't collapse anything, it just splits branches so they no longer interfere. Others, like Copenhagen, treat decoherence as part of the road to collapse, with the environment playing the role of an omnipresent measuring apparatus. Either way, the implication is profound.
Even if no conscious being ever existed, the universe would still be teeming with observations, photons scattering in nebulae, electrons exchanging energy in the hearts of stars, quantum fluctuations interacting in the early moments after the Big Bang. Reality would still unfold in a definite, classical-looking way, at least from the perspective of those systems interacting with each other. This cosmic-scale view also reframes our central question. Do particles exist when you're not looking? If looking means interaction, then yes. They exist in definite forms relative to the other systems they're interacting with. You might not be there to see an electron hit an atom in a distant galaxy, but from the atom's perspective, the event is as definite as the one that happens in your lab. Observation is everywhere, all the time. Some scientists take this even further, suggesting that the very structure of the universe, the web of space, time, and matter, is the result of a kind of self-measurement. Quantum fluctuations in the early universe may have been frozen into definite states by their interactions with the surrounding environment, seeding the cosmic structures we see today. In that sense, the galaxies themselves are fossils of ancient quantum measurements. There's a kind of elegance to this idea. It removes the anthropocentrism of interpretations that give humans a special role. It doesn't require consciousness to flip the switch from possibility to reality. Instead, it treats measurement as an inevitable consequence of being part of a universe where things interact. And yet there's an irony here. If the universe is constantly observing itself, then every conscious observation we make is really just a tiny ripple in a sea of cosmic measurements that have been going on since time began. We are participants, but not the only participants, not even the primary ones. Our role may be less about causing reality to exist, and more about decoding the vast record the universe has already written. Still, this view doesn't completely sidestep the deeper mystery. Even if we accept that environmental interactions act as observers, we're left with the question of what reality is before those interactions take place. In the tiniest, most isolated quantum systems, shielded from the environment in carefully controlled experiments, we can preserve superpositions for astonishingly long times. In those moments before interaction, the particle's properties really are undefined in the traditional sense. No amount of cosmic photon scattering changes that until something finally interacts with it. So perhaps the right way to think about it is this. The universe does not need you to look in order for most of its contents to be in definite states. It has been looking at itself since the first fractions of a second after the Big Bang. But in those rare, protected corners of existence, where systems are isolated from the cosmic web of interactions, the old question still stands. There, the act of looking, whether by you, a detector, or another particle, truly does bring the system into a definite state. And if that's true, then the boundary between looked at and not looked at is not a matter of consciousness, but of connection. In the grand cosmic sense, the universe is a vast, interconnected web of observations, a network where each part is both the observer and the observed. Looking out at the stars, we are seeing the results of ancient interactions, each one a cosmic measurement frozen into the fabric of space-time.
From here, our journey will take one more speculative leap into an idea that merges physics with a metaphor borrowed from our own technological age. If particles sometimes behave as though they only render when observed, could it be that the entire universe operates in a similar way? That it's less like a fixed stage and more like a simulation, computing reality only when needed?
At first glance, the simulation hypothesis might seem like science fiction, the stuff of movies, not physics. The idea is simple, unsettling, and strangely familiar to anyone who's ever played a video game. What if our universe is not a physical stage at all, but a kind of computational construct? A simulation running on some incomprehensibly advanced substrate, where reality is rendered only when and where it's needed. This notion gained mainstream attention thanks to philosopher Nick Bostrom, who in 2003 laid out a formal argument. He suggested that at least one of the following statements must be true. 1.
Civilizations never reach the technological maturity to run realistic simulations of conscious beings. Second, civilizations that do reach that point have no interest in running such simulations. 3. We are almost certainly living in a simulation. His reasoning hinged on scale. If a civilization could create billions of simulated worlds, each containing billions of conscious agents, then the simulated minds would vastly outnumber the original ones. Statistically, the odds would favor us being among the simulations, not the base reality. But how does this tie into our question, do particles exist when you're not looking? This is where the analogy to rendering in a video game becomes irresistible. In a complex game, the computer doesn't waste resources generating every detail of the world at all times. It renders only the parts the player can see or interact with. Everything else remains a simplified model, ready to be fleshed out on demand. In this analogy, the quantum world's strange behavior starts to make a different kind of sense. A particle existing in a cloud of probabilities until observed? That could be the simulation's way of conserving computational resources, filling in a definite state only when an observation, a query from the program's perspective, forces it to produce one. Before that, there's no need for the full detail. A probability distribution is enough. The delayed choice and quantum eraser experiments, which seem to retroactively decide a particle's past behavior, might be seen not as rewriting history, but as the simulation generating a consistent history in response to present events. In this frame, the universe doesn't decide until it absolutely must, and once it does, it fills in the past in a way that keeps the story coherent. Of course, this is metaphor. No serious physicist claims to have found code in the cosmos. And yet, there are curious patterns that make some wonder. The mathematics of quantum mechanics already describes reality as a kind of probability engine, outputting definite results only at the moment of measurement. Space and time themselves may be quantized at the smallest scales, hinting at a pixel-like structure. Even the maximum speed of light could be seen as a kind of processing limit. Proponents of the simulation idea sometimes point to so-called glitches in physics, unexplained coincidences, fine-tuned constants, or deep mathematical symmetries, as signs of underlying design. The standard model of particle physics, for instance, works extraordinarily well, but its structure seems oddly specific, as though optimized for a particular purpose. Our universe's physical constants appear balanced on a knife's edge, allowing for the formation of matter, chemistry, and life. Is this the result of chance, necessity, or programming? Critics are quick to push back. The simulation hypothesis, while intellectually stimulating, suffers from a lack of testable predictions. Any evidence could be dismissed as simply part of the simulation's design, making it unfalsifiable. Others argue that invoking a simulation just moves the mystery up a level. If our reality is simulated, who or what built the computer it runs on, and is their world simulated too? Still, the idea resonates because it offers a kind of narrative closure to the oddities we've explored. The observer effect, rendering optimization, decoherence, the program locking in certain details once they're interacted with, non-locality, instant synchronization of data across the system. In this metaphor, reality's strangeness is not a bug, but a feature, the signature of a system designed to give the impression of a continuous physical world while managing its own complexity behind the scenes. And if we were in such a system, would it matter? From inside the simulation, the rules we observe are our reality. Our lives, choices, and discoveries are as real to us as anything in a base world would be to its inhabitants. Even if the stars above were lines of code, they would still be the stars by which we navigate. There's a poetic symmetry here. The earliest human thinkers imagined the world as a stage crafted by unseen hands. Today, our most cutting-edge physics occasionally circles back to a similar question. Could there be a hidden architecture behind the curtain of reality? The simulation hypothesis doesn't claim to answer how or why we're here.
It simply proposes that what we think of as fundamental may be the user interface of a deeper reality. Whether metaphor or truth, it reframes our original question in the broadest possible way. Do particles exist when you're not looking? If the simulation analogy holds, then particles exist in the same sense that the unseen parts of a game world exist, as potential data ready to be called into full resolution when needed. The rest of the time, they are possibilities stored in the system's underlying code.
Even if we never find proof, the exercise of thinking this way can be valuable. It forces us to see the assumptions we carry about reality, that it's continuous, objective, and always fully there, and to realize how deeply those assumptions are challenged by the quantum world. But eventually we have to step back from speculation and return to what we know. Across all interpretations, Copenhagen, many worlds, relational, consciousness-based, decoherence, simulation, one truth remains: the boundary between the possible and the actual is not where classical intuition tells us it is. And that truth leads us to our final step, the conclusion that gathers these threads into a single, if incomplete, answer. We began with a simple, unsettling question. Do particles exist when you're not looking? It sounded like a philosophical riddle, the kind of thing you might idly ponder and then dismiss. But in tracing the experiments, interpretations, and implications, we've found that it is not idle at all. It is a question physics has asked of the universe directly, and the universe has answered with something stranger than any parable. From Thomas Young's double-slit experiment to the modern refinements of delayed choice and quantum erasers, we've seen that, in the quantum world, the line between possible and actual is not fixed. Particles can act like waves of probability until some kind of observation, whether by a human, a machine, or the environment itself, forces them to commit to a specific outcome. The timing of that observation, and even the availability of the information, can shape what we see, sometimes appearing to rewrite history to maintain internal consistency. We've walked through the spectrum of explanations physicists have offered. Copenhagen, with its pragmatic acceptance that reality is undefined until measured. Einstein's realism and his refusal to accept a universe ruled by chance.
Bell's theorem, which shattered the dream of local hidden variables and showed us that non-local connections are woven into the fabric of the world.
Many worlds, where nothing collapses and every possibility happens somewhere. Relational quantum mechanics, where reality is a patchwork of perspectives that become consistent only when connected. Consciousness-based views, daring to suggest the mind itself may be part of the machinery of measurement. The cosmic observer, in which the universe constantly measures itself through an endless web of interactions. And finally, the simulation hypothesis, where reality's rendering on demand may be the logic of an even deeper system. These interpretations disagree, sometimes violently, on what's really going on. But they agree on this. Our classical intuition about a world that exists with definite properties at all times, independent of observation, does not survive the quantum test. In the places where our measurements can reach, reality is cooperative and concrete. But in the spaces we haven't looked, and in the instance before interaction, reality is something else. And that something else is not just an absence of knowledge. It is a different state of being, one that resists our ordinary categories. Not hidden facts waiting to be found, but facts that are not yet facts. A world in potential, waiting for the spark of interaction to ignite into a definite form. So, do particles exist when you're not looking? If by exist we mean have definite observer-independent properties, the most honest answer physics can give is not always. Sometimes they exist as a spread of probabilities with every possible outcome still in play. Sometimes their existence depends on the relationship to something else, an atom, a detector, a human mind. And sometimes, according to certain interpretations, they exist in all possible forms simultaneously, each in its own branch of reality. In the Copenhagen view, the audience of reality is whoever or whatever makes the measurement. In many worlds, reality doesn't need an audience at all. It simply unfolds into countless versions. In relational quantum mechanics, there is no single universal stage, only interconnected perspectives. In consciousness-based ideas, the audience may literally be you. And in the cosmic or simulation frameworks, the audience is everything, everywhere, all the time, or the hidden architecture in which it all plays out. There's an irony in this. We began by asking whether reality exists without us. We end by seeing that, in some interpretations, we are not just passive spectators, we are participants. Even in those interpretations that minimize our role, we are still nodes in the great network of interactions by which the universe observes itself. Every measurement you make, every experiment performed, every photon that bounces into your eye becomes part of the record of what is real. And yet the mystery remains intact. Quantum mechanics is not coy. It gives us equations that work to extraordinary precision. But it is reticent about telling us what those equations mean in terms of reality itself. We can map the probabilities, but the underlying nature of the world when we are not looking, still lives behind a curtain. Perhaps that is the final lesson. The universe may not need us to exist, but our curiosity, our relentless urge to look, is what transforms it from a set of possibilities into a lived experience. We are, in a sense, the universe's way of turning potential into story. So, as you sit here now, consider the room around you. The objects in your sight are concrete, definite. Beyond your vision, in another room, the details are less certain. Further still, across the galaxy, particles collide in ancient stars, their outcomes fixed by interactions long past. And further yet, there are events that have not been decided in any frame, still floating in the liminal quantum haze. You are part of the audience that makes some of those decisions real.
And maybe, just maybe, there's something poetic, even beautiful in that. We are not the whole audience of reality, but we are in the front row for our part of the show. We look, we measure, we participate, and when we turn our gaze away, the rest of the cosmos continues its endless, intricate dance, deciding for itself, or for no one at all, what will be.
If the universe needs an audience, it has one. If it doesn't, we are still here, watching, wondering, and in our own way, helping reality take shape. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.